All right, here we are again. So now, of course, today's Wednesday. This will be our last meeting of the week. We'll meet again next Monday. In the meantime, we're going to go back to Chapter 7, which is our discussion about the normal distribution, which we really just got started on. I was really just setting up the background for what exactly is a continuous probability distribution. But now we want to focus our attention on the properties of the normal distribution and get some practice using it to calculate probabilities. And I did mention last time that the normal distribution is actually maybe the most important distribution that we'll do in this class. It is used in many, many different applications in statistics. And in fact, unlike the binomial and the Poisson, which we only see in Chapter 6, the normal distribution will continue to show up throughout the rest of the course because it's that important. Okay, so now we have a few options here for calculating probabilities with the normal distribution. There are calculators such as the TI-8384 series where the functionality is already built into the calculator. But if you don't have that calculator, you can always use tables. Now, tables have been around for forever and they work very well, but if you do have the more advanced technology available to you, you might want to lean on it. At the very least, use it to double check your results. Okay, so the instructions for using the TI-83 and 84 are in these slides if you want to use them. If not, we'll use the tables. Okay, so let me go get the tables as well. So it turns out there's two of them. One is meant for positive values and one is for negative. Now, let me get this out of here. Obviously, that's an old example. You can just delete that yourselves. Oh, here's another one. Because if you are using Adobe's Acrobat Pro DC, like I am, you can actually write on your PDF files. If not, you should still be able to delete any markings that are still left on there. So anyway, so this is the positive table. And then we also have the negative version. And we'll see very soon how these are used to help us calculate probabilities. Okay, so then let's go back to the slides and let's see, where did we leave off? So we start out with a lot of theoretical discussion about how continuous distributions are different than discrete distributions. The main difference is that with a continuous distribution, we have an infinite number of possible values. Whereas with a discrete distribution, the number of possibilities is finite. Now, it can still be a very large number, but it's not infinite. So like, for example, when we were rolling dice and flipping coins and that type of thing, it's obvious that we cannot have an infinite number of flips. We can't roll the dice an infinite number of times, and the outcomes are restricted to being positive integers. So it must be the case for those examples that they are described by a discrete distribution, such as binomial or possibly Poisson. But now we're looking at situations where the outcomes themselves can have a fractional component, such as the time until the next phone call. And what that does is all of a sudden you have an infinite number of possibilities, which we did not have before. Okay, so that changes the way we do our calculations. Instead of taking the formula and plugging in numbers, the formulas in this chapter are more involved and they do require the use of calculus for us to implement them directly. So we won't be doing that here. Instead, we'll be using the tables or else the calculators. Now, if you were taking this class in the math department, you might have to do the calculus anyway, but we're not in the math department. This is the economics department, or actually, no, it is the math department, but we're focused on economic applications. So we're not going to prove anything. We're not going to derive anything. We're going to use the techniques that are the most straightforward for us to use, because our focus here is more on the applications than the actual math itself. So anyway, hold on one second. There we go. So let's jump ahead. We already have discussed how a continuous distribution is different. So let's go back and revisit the normal distribution. Now, we did mention a few of these key details already. Number one, if you notice, now we're looking at a curve rather than a histogram. You can't really use a histogram to describe a continuous distribution because it would require an infinite number of bars. So instead, what we're essentially doing here is we're imagining that we have an infinite number of bars, and the curve basically connects the tops of those bars. Okay, that's really what we're seeing here. In fact, I tried to draw this, I think, back here somewhere. Yeah, I mean, you have to visualize that you've got all these bars, an infinite number of bars all crammed together. And so it's not really feasible to show the bars. What we have to do instead is imagine that we're just simply connecting the tops with this curve. And because there's an infinite number of bars, the curve itself is smooth and continuous. And it will also have its own formula. In this case, I showed you the formula for the normal curve. And, you know, it doesn't look on the surface all that terrifying, but the idea here, though, is that in order to use it, you would need to use calculus rather than plugging numbers directly into it. And so that's why we prefer to avoid that step and instead go ahead and use either our calculators or our tables. So the curve is smooth and continuous. It goes out to positive and negative infinity. So therefore, it covers the entire real number line. In the middle, we have this Greek letter mu, which represents the mean of the distribution or the center. And the areas on the right and the left are mirror images of each other. In other words, the distribution is symmetrical about the mean, which is a nice feature because, as you'll see when we're doing our calculations, that can help us tremendously because it does reduce the amount of time we need to calculate some of the probabilities, at least. Not all of them, but in some cases, this will be very, very helpful. Also, one more detail, the area under the curve equals 1. The formula, it may not be obvious from the formula, but it is defined to ensure that the entire area under this curve is exactly equal to 1. Because even here, with an infinite number of possible values, we still have to follow the axioms of probability. So the axioms tell us that the total probability is always equal to 1. And so that has to be the case here as well. And one of the nice things about this is that because the area is exactly equal to 1, that means probabilities and areas are actually the same thing. So when we're calculating probabilities, what we're really doing is calculating areas under this curve. And so the two mean the same thing in this context. So here's the formula, and I just wanted to point out here that the two values that uniquely identify this distribution are the mean and the standard deviation. In other words, mu and sigma. If we know the values of mu and sigma, that gives us all the information we need to fully describe that particular version of the normal distribution. Okay, and I showed you a couple of graphs to illustrate why this is the case. Let's see, where are they? Here we go. Well, first, this is what the curve in general looks like, but if we had two normal distributions with the same standard deviation, but different means, they'll have the exact same shape, but the one with the higher mean will be located further to the right than the one with the smaller mean. So in other words, the mean determines the location on the real number line. The shape is the same. Okay, and you notice the tails do go out to positive and negative infinity, no matter where they're located. The thing that separates one from the other is where is the center, or where are they located. But on the other hand, if we have two normal distributions that have the same mean but a different standard deviation, then the shapes are different. Now, although both of these curves still have that same basic bell-shaped curve, they're still technically bell-shaped curves. The one in the center with a very low standard deviation of only a half is very tall. And if you notice, most of the area is concentrated fairly closely to the mean. Whereas with the second one, it's very short, but it's much more spread out. Okay, so in the second case, the standard deviation is 10. And that just means that the values are more spread out, which means you're more likely to get very large or very small values than you are with the the case of the smaller standard deviation. But the basic properties never change. In other words, each curve has an area of 1. They're both symmetrical about their mean. What's different is the way they're spread out. So those two features, the mean and the standard deviation, uniquely characterize the normal distribution. There's an infinite number of normal distributions, each with its own unique value of the mean and the standard deviation. And in fact, you know, if it was impossible for any two people to have the same first and last name, we could sort of think of this as your first and last name. You know, you can have, let's say, multiple people with the same first name, but not the last name, but not both. If that was the case, it would work very similarly to this, because then knowing somebody's first and last name would mean we know who this individual is. But since we can have people with the same name, that analogy sort of breaks down. But you could maybe imagine instead that, I don't know, the mean could be your social security number, and the standard deviation could be your purchase ID, let's say. And then having those two pieces of information means we can uniquely identify who you are. But here it's the mean and the standard deviation. So all probability distributions basically are an infinite class or family of distributions. You might recall that we looked at some histograms for the binomial distribution, and in each case we changed the value of pi, and we saw that it made a significant difference in the appearance of the histogram. If we had done the same thing with n, we would have also seen that the graphs look different. So with the binomial distribution, the two values that uniquely characterize it are n and pi. So here we say that there's an infinite number of binomial distributions, each of which is uniquely characterized by the values of n and pi. With Poisson, there's only one value that uniquely characterizes it, and that would be lambda. So the normal distribution is uniquely characterized by two values, the mean and the standard deviation. And since there's an infinite number of possible values of mu and sigma, that means there must be an infinite number of normal distributions. So it's not just a single distribution, it's actually an entire infinite set of distributions. And we did also mention that one of these infinite numbers of normal distributions is so important that it actually gets its own separate name. And that would be the standard normal distribution. And here we have a mean of 0 and a standard deviation of 1. And the reason why this is the so-called standard normal is because it is easy to interpret it, as we started to do yesterday. And in fact, it's so important that this table that we're about to look at, that I briefly mentioned before, is based on the standard normal. In fact, it even says in the top there, the standard normal, to make sure you know that this is not just any old normal distribution we're looking at. This is the standard normal. Same thing here for the negative table. All right. Now, it turns out that if you're dealing with a different normal distribution, you can still use this table, but only after you've made a transformation, which we will discuss later on. So the table, even though it's meant for the standard normal case, in principle, it can be used for any normal distribution that you might encounter. If that weren't the case, we would need an infinite number of tables to cover all the possibilities, and that would be very awkward, to say the least. But it's not, it'll turn out it's easy to transform any other normal distribution into this version so that we can use our tables. Anyway, I did also mention notation-wise, we tend to use X to represent random variables. We've been doing this all along. Like with the binomial, remember we used X to represent the binomial random variable. With the Poisson, we did the same thing. In this one special case though, by convention, we're going to use the letter Z to represent the standard normal distribution. We'll use X for all the other normal distributions, but we'll save Z for this one case. And I don't know who came up with this idea, but this is something that everybody uses in statistics. It's understood that Z refers to the standard normal. X can represent any of the others. And so you may have heard this term Z-score, which is taken from the standard normal distribution. And we'll be seeing how that works as well. All right. Now, we started to briefly look at some of the properties of the standard normal distribution. And you can see based on these numbers, because this is the standard normal distribution, 0 is the same thing as the mean. In other words, that 0 there is the mean of the distribution. Because the standard deviation is 1, 1 in this context actually means 1 standard deviation above the mean. And similarly, -1 means 1 standard deviation below the mean. Now, one of the properties of the normal distribution, the standard normal, I should say, is that roughly two thirds of the area under this curve falls within 1 standard deviation of the mean. That's the shaded region. Now we'll double check this with the tables as we go along. But it turns out that based on the shape of this curve, the area within 1 standard deviation of the mean accounts for about 2/3 or 68% of the entire distribution. If we stretch that out to 2 standard deviations, that will cover about 95.44% of the cases. So at this point, yesterday I created an example so that it might seem less abstract. Imagine, for example, you were told that rainfall is normally distributed, the mean is 40 inches per year, and the standard deviation is 5. Actually, let me do one thing here. Just a quick reminder, since I have access to all these wonderful symbols, why not put them to good use? By the way, you can do the same thing too. If you're typing a document on Word, let me show you, actually, in case you're really going to do this, let me show you a really helpful hint here. This is just, I've decided to give you a 2-minute word lesson, or actually a word PowerPoint lesson. Imagine the following scenario. You've got an a PowerPoint presentation, and you need a special symbol. All right, let's say that for some reason you're typing a document and you need the Greek letter theta. All right, so, and you say to yourself, well, I'm going to go to the insert symbol box, but I can't find theta. Where is it? Now, the thing about the symbol boxes is that they're not terribly well organized, in my opinion. You might waste a lot of time looking. By the way, it's this one. But what I wanted to point out to you is this. Every one of these symbols has associated with it a special type of code, which is called Unicode. Now, if you notice right here, it's listed as 03B8. So what happens here is that if you type 03B8 and hit Alt-X, oh, I just realized that only works in Word. Oh no. All right, so here's what you'd have to do. Sorry about that. This is starting to seem like a headache, but let's try that again. 0B38. And what I do is hit Alt-X. Oh, see, now what happened there? That is not what I was expecting. All right, let's try this. Let's go to the internet. Unicode for theta. Let's say it is, oh, you see, it says here that it is O3F4. Huh. There it is. Okay. And then you can copy and paste it back into a PowerPoint. I don't know why this doesn't work in PowerPoint, but it works in Word. and you can then copy it into your PowerPoint presentation, because sometimes finding symbols is a real headache. You can search all you want, and sometimes it just is so hard to find it. So if you really need to use symbols, and it's not just Greek letters, they have all kinds of other stuff in here too. As you can see, like, I have no idea what that thing is, but if you need it, you can either insert the symbol and look for it manually, or you can look for the Unicode symbol. Just saying, in case it shows up. One day you might have to write a paper in statistics, in a more advanced statistics course or something, and it'll be helpful to be able to use this stuff. All right, anyway, so let's get back to this. The mean rainfall is 40 inches, the standard deviation is 5. Now, that means that, in fact, you know what I should do here? Let me draw a separate picture so that it's even more crystal clear what's going on. We were told that the mean is 40 and the standard deviation is 5. So I'm choosing these values for a reason. All right, I'll tell you, let me do this a little differently. Let me just write these numbers. So what that implies is that this is the mean plus sigma. So with the standard normal, this would be equivalent to 0, 1, 2, minus 1, minus 2. Okay, let's call this x and this is z. Well, guess what? We were just told that 95% of the distribution falls within 2 standard deviations of the mean. So what that tells me is that the probability that the rainfall next year, hold on. The probability of the rainfall being between 30 and 50 inches is 0.9544, because that represents being within 2 standard deviations of the mean. So you see, even though the rainfall is not standard normal, it is normal but not standard normal, we can still use the information we have about the standard normal to figure out our probabilities, because what we're basically doing is reducing each of these numbers to a given number of standard deviations above or below the mean. So I would compare this with the conversion between Celsius and Fahrenheit. You know, for example, that when it's 0 degrees Celsius, it's 32 degrees Fahrenheit. Now, both of those temperatures represent the freezing point. It's the same information. The numbers are different, the units are different, but it's the same information. It's the same temperature. It's the freezing point. So effectively, we're doing the same thing here. We're converting from one scale to the other by reducing everything to standard deviations. And so this approach will make it possible for us to use our tables for any any normal distribution we may encounter. All right, so don't worry, we'll get plenty of practice with this. If it seems bizarre and abstract right now, we'll get plenty of practice, and after a while, you'll be experts in doing this. All right, and then the last case that we probably should be familiar with is, what about plus or minus 3 standard deviations? That brings us to about 99.7% of the entire distribution, which means there's almost no area outside those two values. The unshaded regions here collectively contain only about 0.3% of the entire distribution. Now, of course, most of the time our probabilities will not fall exactly into one of these three categories. So we have to have the ability to do other kinds of calculations. And so that's where the tables will come in so handy. All right, so why don't we do some examples with the tables? We're going to start with the standard normal distribution. Okay, let's assume that whatever we're working with, it follows the standard normal distribution, and we want to gain some insights into how these tables actually work. Okay, so first things first, all the probabilities in that table are what we call cumulative probabilities. Which is just another way of saying less than or equal to probabilities. They mean the same thing, okay? Less than or equal to is known as a cumulative probability. So let's say that you see this curve up here. This is the standard normal distribution. And suppose that for some reason, and remember that is designated with the letter Z. What if I need to know the probability that Z is less than or equal to 1? Well, what I'm basically doing is calculating the area of the shaded region under this curve. But how do I do that? Well, that's a good question. And by the way, don't forget, this represents one standard deviation above the mean. I need to know the probability that our Z here is less than or equal to 1. And that 1, by the way, is often known as a Z-score. Well, what I'm going to do is go to my table. Now, the table is set up. We have to be careful about the way the table is set up. It has information on, let's go look at it for a second. Two critically important pieces of information. The top row and the first column contain what we're looking for. Okay, so what we're effectively going to do is combine what's in this first column with what's in this top row. And so what's happening here is that the first column shows, let's say you have a number like 2.17. This piece comes from the first column. This 7 comes from the top row. Actually, let me make that a little cleaner. This is a PDF is pretty powerful, but in some ways it's very frustrating because, there's a lot of features that are not the least bit clear how to do them. It took me a long time to find this eraser, let me tell you. But anyway, so let me try that again so you can really see it better. That number comes from the first column, and this number comes from the top row because 2.17 can be written as 2.10, or just 2.1, I should say, plus 0.07. Now that's the key. So if I come over here to this table, and just shrink it up a little bit so you can see what I'm doing. Oh, that's a little small, but all right. I probably shouldn't have picked such a large number, but you see there's a 2.1 here, and there's a 0.07 here. And the intersection of those two is right here. And that number is, well, let me make it a little, oh, here we go. You can see that, I think. The 2.1 is over here. The 0.07 is here. And at their intersection, we find what we're looking for, which is 0.9850. And that is our probability. So in other words, if this was 2.17 in this picture, that shaded region would be 0.9850. And what that means, and the way we interpret that, is that the probability that z, the standard normal random variable, is less than or equal to 2.17 is 0.9850, or if you want to, you can think of this as 98.50%. So don't worry, again, like I said, after you've done a few of these, it'll be second nature. So you've got this number, 2.17. We want to know the probability of being below that value. So to look it up in the table, we need to break this up into two pieces. The first two digits are the first column. The last one is the top row. Where they intersect is where we find our probability. Okay, 2.17. Okay, so why don't we do another one just to make sure that we really get it? Let me just quickly save this one. So that I can erase it without losing the results. Okay, so now I'm going to erase it now so we can go on to the next one. Or actually, even better yet, I'm going to reopen it. Oh, see this one, I should have erased this. I'm sorry about that. Let me, I forgot that this is still here. All right, let's try another one. How about if we're looking for the probability that z is less than or equal to 0.87. Okay, now 0.87 can be written as 0.8 plus 0.07. So now what I'm looking for is the intersection of 0.8 and 0.07. Oh, 8078. Well, that wasn't so bad. So that means the probability that z is less than or equal to 0.87 is 0.8078. Okay, well, how about this one? (1.03). What do we do with that one? Well, 1.03 is the same thing as 1.0 plus 0.03. So first, let me erase these guys. Oh, whoops. So we look for the combination of 1.0 in the first column and 0.03 in the top row. Here we are, 0.8461. So that's the basic logic behind these tables. We're looking for a cumulative probability, and the way we find it is by looking for the first two digits are going to be found in the first column, and the last digit will be found in the top row. The table only goes up to about 3.0 something because after that, the values are very close to 1. Now, it turns out that sometimes we may have negative values. So let's look at this one. Let's try negative 2.46. So what's different now is that the 2.4 comes here, the 6 is here, and we find that that one is 0.0069. So on the negative side of the table, these probabilities, as you can see, are very, very small. Typically, not all, I mean, some of them, but let's put it this way, all of the negative probabilities are less than a half. So these are typically very small numbers. All right, so now that we got a feel for how this table works, let's go back to the slides and see some more examples. For example, now here I've reproduced a small portion of it. For the case of 1.0, this is pretty straightforward. 1.00 is the same as 1.0 plus 0.00. So you would go to the table and look for the intersection of 1.0 and 0.00, and you'd end up with 0.8413, which means 84.13%. That's the probability that Z is less than or equal to 1. Okay, well, now we're starting to get pretty good at this, I think. Here's my Excel graph. It's okay, I guess. And you're seeing that you're shading everything from 1 down to negative infinity. Oh, here's a good example, negative 1.13. Well, we've got the negative 1.1 and 0.03. Now you can see from the graph, that's going to be a very small probability. So we go to our negative table and we look at the intersection of those two numbers and we'll find a result. Okay, so I've reproduced it here so you can see it better. Negative 1.1 is combined with the 0.03 and there we go, 0.1292. All right. Now, it seems like so far everything is going great, and it is. The problem, though, is that there are other probabilities that we have not yet addressed. For example, what if the probability of Z is greater than a constant that we're looking for? Or what if it's the probability that Z is in between two constants? We have to make some adjustments to calculate the other types of probabilities, which are not cumulative. But it won't be that difficult. You'll see pretty quickly that it makes perfect sense, and it involves the properties of the standard normal distribution. So let's just quickly review them. First of all, the area under the entire curve, as we've already seen, is equal to 1. This is the formal statement of that. The graph, on the graph, we just are essentially showing that the entire area up to positive infinity, down to negative infinity, is equal to 1. This is required by the axioms of probability. It just means that Z has to be somewhere on that real number line. Okay, so that's pretty straightforward. But here's an interesting consequence of this. Because of the symmetry of the distribution, meaning the left-hand side of the mean and the right-hand side are identical to each other, if the entire area under the curve is 1, then it must be true that the area below 0, in other words, all of the negatives, have a collective probability of a half. And the same thing is actually true too for greater than 0, meaning the right-hand side of this graph. Okay, because these two these cover all the possibilities. Because that's it, that's all we have to choose from. So each one individually has an area of a half. The total is, of course, 1. And this is necessary because of the symmetry of the distribution. The left and the right-hand sides are mirror images of each other. I guess what I should say is, all right. So the only way they can be mirror images is if they both have the same area. And the only way they can both have the same area and yet both add up to 1 is if each individually is equal to a half. All right, well, here's the Excel version of that. Now, here's an interesting one. This, by the way, this little z is some constant or other. Because the area under this curve is 1. Let's say, let's let z equal to, I don't know, 1.2. So this is the result that we need to calculate greater than probabilities. This shaded region is the probability that z is less or equal to 1.2. And this region up here is the probability that z is greater than or equal to 1.2. So the important detail here is this. Both of those cover the entire normal distribution. So they must add up to 1, which implies that algebraically, oh, here we go. This is the key right here. So that means if you need to calculate a probability which is not less than or equal to, but greater than or equal to, this is how it's done. You're basically taking 1 minus the cumulative probability, which you can find in the table, and that becomes your greater than or equal to probability. So now that's one of the consequences of the entire area being exactly equal to 1. Very interesting, very clever. That's how so that's why the tables only have to show less than or equal to probabilities, because it's understood that you can also figure out the greater than or equal to probabilities just by using this approach. All right, now let me just quickly remind you, we just earlier calculated the probability that z is less than or equal to 1. Just quickly remind you, to be 0.8413. We did it the normal way. We looked at the table. So what we're going to do now as an example of this is calculate the probability that z is greater than or equal to 1. So the table, now we're looking for this. But the table tells us this. And we saw earlier that it's 0.8413. So algebraically, that implies that this must be equal to 1 minus 8413, or 1587. Okay, so that's what we have right here. So the part that we actually wanted is 1 minus the part that's on the table. So what we do this in 2 steps. We figure out the probability that z is less than or equal to 1. And then whatever that is, we subtract it from 1. And that gives us what we're actually looking for. All right. So all the greater than or equal to probabilities will be done in exactly the same way. Well, now here comes another example. Okay, now this one involves a negative number. So it's not that much more difficult. I think, it's harder to think in terms of negative numbers, but still, you'll see that everything works the same way with the negatives and the positives. So here we're looking at negative 1.59. So we're after this area, but we can't look that up directly. Having said that, though, what we can do is find this on the negative table, which we will do. We go get it. Negative 1.59. Oops, not that one. Actually, we'll just write it as negative 1.5 combined with 0.09. Here's the negative 1.5. Here's the 0.09. And that area is 0.0559. And it's small, as we expected. It's a very small number. By the way, I just want to point out that I don't know if they're being consistent here. These technically should be negatives, but it's understood, I guess, that these are all negatives. I'm not quite sure why they do that. But anyway, 0.0559, I find it a little annoying. But 0.0559, we can come back here now. So that area that we can find in the table is 0.0559. So therefore, the area that we're actually interested in must be 1 minus 0.0559, which is 0.9441. A pretty large number. As you can see, it covers most of the distribution. All right, so what this means is that now we can calculate any less than or equal to probability from the table, and with a little rearrangement, we can calculate any greater than or equal to probability. But there's one more case that we need to understand, and that's the case of probabilities that are in between 2 points. What do I mean by that? What if, for example, I want to know the probability that z is between 1 and 2. Oh, now that's a tricky one. Well, we're not going to find this in the table, that's for sure. But there's a way we can work around that. What we're going to do is this. Actually, I need to draw this one more time. Let me see if I can do it this way. The strategy here is to basically take the larger area and subtract the smaller area. Now, I don't know if we had like clay that we were working with, we can show this much more easily. We could take the big piece and take away the smaller piece and see what's left over. I'm trying to help you visualize this, but what we're actually doing here is saying that this probability between 1 and 2 is actually obtained by taking the probability that z is less or equal to 2 minus the probability that it's less or equal to 1. I don't know if this graph is helping or not. From down here, in other words, you're taking this probability and you're subtracting this one. So that what's left over is the piece that you actually need. And of course, these two probabilities are cumulative probabilities. We can easily look them up in the tables. So why don't we do that right now? All right, let me create a new graph here. I don't know if this, for some reason, this one is very difficult to draw. Let's see what we can do here. Maybe I'll use different colors. Use black for less than or equal to 2. And then we'll switch to red for less than or equal to 1. So the part that we want is the part that's only shaded in black, only, not the red. Okay, so this is going to be subtracted from this. So we can look these up in the tables, but remember, we need 3 decimals. So what we're going to do is write this as 1.00, and we'll write this one as 2.00. So we'll go back to the table for, now 1 we've already seen. 1 is easy. We're looking for, okay, I guess looking is this one, the intersection of 1, 1.0 and 0.00. Okay. So, oh, I made it too big that time. No, you can probably still see it. It's right here, 0.8413. Now for 2, it's 2.0 plus 0.00. So we scroll down a little further. It's way down here. 2.0 and 00 is right here. 9, make it a little bigger now. 9772. I circled them too big here. Hold on. All right, that's better. 2.0 combined with 0.00 is 0.9772. So we need the difference between them. Okay. So let's copy this back to the slides. Oops. 9, yes. So I'm just going to copy what we just did, 0.8413. So the probability that z is between these 2 points 0.9772 minus 0.8413. 1359. This area in here, which you're actually interested in, is 0.1359. Wow, that seemed like a lot of work, but not really. You're just taking the difference between two cumulative probabilities. And they, by the way, they can be positive or negative. That doesn't matter. Well, with all that being said, let's try another example. First, I'll give you a minute to catch up here. Now, you don't, by the way, you're not required to draw these pictures. There, you might want to think about doing it if it helps you visualize what's going on, but they're not mandatory. So when you hand in the problem set for this chapter, it's not going to ask you to draw any pictures, but you certainly can feel free to do so if you want to, especially when you're in the beginning, when you're first learning this stuff. I find that they're very helpful. Well, now we have another case, two different positive numbers, two that we've not used before, so that's kind of fun. Let me go get the positive table. All right, I'm going to reopen that. So I don't have to keep erasing every time. There we go. So it looks like we're looking for the probability of being between 0.72 and 1.83. Oh, whoops, what am I doing? Sorry, it's 0.872 and 1.83. Now, since this is an in-between probability, that means we're going to solve it like this. By the way, if you get these two backwards, you'll just get the right number, but with the wrong sign. But remember, you're aiming for the larger probability minus the smaller probability. And so these two come from the table. Let's confirm this now. Let's go look up 1.83, which of course is 1.8 plus 0.03. Just for the practice. Here's the 1.8. Here's the 0.03. That turned out to be 9664, correct. And the 0.72, of course, we can find it as 0.7 plus 0.02. Let's go back and find that one. 0.7 combined with 0.02. 7.7642, yes. So now when we subtract these, we'll get the answer we're looking for, which turns out to be 0.2022. And we're done. That's all we had to do. Man, so really there's only three cases you have to worry about: less than or equal to, which is on the table; greater than or equal to, where you subtract, it's one minus the opposite, or less than or equal to; and the in-between ones where you're subtracting one from the other. So well, it seems like a lot right now, but it really isn't, because there's really, when you come right down to it, only the three basic cases. And one of them is already on the table. So, you know, it's really, it's not that bad. All right, let's do another example where the two numbers are both negative. We're going to have a probability where z is between two negative numbers, but the process is exactly the same. The only thing that changes is that you're looking at the negative table. The other part, the subtraction, is still the same, but you just want to make sure you're taking the larger number minus the smaller number. That's the only thing you have to watch out for. All right, so let's take a look at this thing. All right, how about negative 2.05 up to negative 0.67. So now, by the way, in this case, it's the negative 0.67. That's the larger of the two probabilities. It looks backwards, but that's correct. So we've got these from the negative table, which we will confirm right now. Let's start with negative 2.05. So I want negative 2 combined with 0.05. 0.0202, that means we did that correctly. How about negative 0.67? I need to find negative 0.6. Whoops. There we go. See, sometimes this is the only awkward part about this table. The 0.7 is here. 0.07 rather. So now I've got to find the intersection between them. And it is actually right here. I know it's hard to see it because it's way up here. That's the 0.07 that we need. That's the point, negative 0.6. So the two bring me to 0.2514. So that one has been done correctly. And then you just subtract. And that turns out to be 0.2312. And that's it. Finally, there's one last case we want to look at. It's again a between problem, but one number is negative, one is positive, but again, it makes no difference. The process is exactly the same. All right, I'll give you a minute to catch up, and then we'll do one last example. All right, let's try it. One more. Oh yeah, what do you know? So yes, we can do between positives and negatives, no problems there. Between negative 1.04 and positive 1.33. So as usual, we'll simply look up the two individual probabilities and then subtract. All right, so let's confirm this 1.33. Let's get all this stuff out of here. 1.33 is the combination of 1.3 and 0.03. There we go. 0.9082. Is that what we found here? Yes. Okay. Now for the negative, I have to go to the other table, negative 1.04. Get this stuff out of here. I find it to be distracting here. What was it? Negative 1.04. So we have negative 1.0 combined with 0.04. And that brings me to 0.1492. Oh, yes. Okay, so all we have to do is subtract. And that gives me 0.7590. Excellent. So now you are all experts in using these normal tables. There are no other cases that you could encounter with these normal tables. That's it. You covered all the possibilities. So you should never, ever have a problem calculating any normal probability that comes along. Now, having said that, though, remember, all of these cases assume that we are looking at the standard normal distribution because that's what the tables are set up to do. What about all the other cases where we're dealing with a normal distribution, but not the standard normal distribution? Well, this is what I was talking about before, Celsius and Fahrenheit. If you have a normal distribution that is not standard normal, you can use a formula to convert it into the standard normal case. And it's a very easy formula. And once we've done that, we can then continue to use the table. Just like I said, it's really equivalent to converting Fahrenheit into Celsius. I guess you can think of the normal table as Celsius and all the other cases as Fahrenheit. So we convert everything to Celsius and then we're all set. Just like in the real world, every other country on the planet uses Celsius except us. So anytime you go outside of the United States, you've got to convert those temperatures in your mind from, well, you're converting Celsius back to Fahrenheit, okay. But if you've ever been abroad, you know what a nuisance it is. You got to get used to it. All right, anyway, so watch how simple this formula is. Suppose that X is a normal random variable with a mean of mu and standard deviation sigma. Now, we'll, of course, supply those numbers. Then, in order to convert X into Z, look how easy this is. It couldn't be much simpler than that. And what the number you get now is often referred to as a Z-score. In fact, all of these what we're looking for in all these other cases are anytime you have a standard normal random variable, it is often called a Z-score because it's based on the standard normal distribution and it can be interpreted as a certain number of standard deviations above or below the mean. For other cases, you don't have that easy interpretation. So here we can take any normal random variable and turn it into the standard normal case so that we may continue to use the tables. All right, so we transform it, X into Z. Now, by the way, if there's some reason why you need to do the opposite, you can rearrange this formula algebraically. Although I don't think we'll need to do this. It goes both ways. If you have a standard Z-score and you want to convert it to the original X, you can do so this way. But this is the one that we'll be using. That's a biggie. All right. Now I'll tell you what, since it's awfully close to 11:15 or normal break time, why don't we stop here before we do our first example, where we're basically taking a normal case, which is not standard normal, and we're using the tables to calculate probabilities after applying this transformation. All right, so I think this is a logical stopping point. And when we get back, we'll do these and we'll do some more examples. And then I'll show you an interesting application of all of this stuff. But all right, let's knock it off for a bit. Let's come back around 11:30 when you have lots of, well, you'll be plenty happy because hopefully you'll had something fun to eat or drink in the meantime. And we'll dive into all these wonderful examples. All right, so see you in a little bit. Ah, all right. Hold on. All right, I guess we're ready to start again. So what we're doing here is taking cases where we have a normal random variable, which is not necessarily standard normal, and we're going to use this conversion formula to come up with our probabilities. All right, so imagine the following situation. We have a stock that is normally, whose returns are normally distributed, and the mean is 5% per year, and the standard deviation is 2%. Now, what this means then is that the returns to the stock are normal, but they're not standard normal. So what we can do is represent this random variable with an X, and we'll just say that X is normal with a mean of 5% and standard deviation of 2%. Now, when we're dealing with percentages like this, by the way, we're going to actually convert them into decimals. I just find that it's easier to work with them that way. The units are not really that important as long as we're consistent with them. Now, with this information in hand, we're going to calculate 3 different probabilities. Given that the stock on average gives us a return of 5% per year with a standard deviation of 2%, we'd like to know the following 3 probabilities. A, that over the coming year, the return is 4% or less. B, 8% or more. And C, between 4 and 7%. All right, so now let's start by doing our conversion or looking at the conversion formula. And so because the mean is 5%, which we will write as 0.05, and the standard deviation is 2%, which we will write as 0.02. For each of these problems, we will apply this formula. In other words, we'll take whatever value we're being asked for, we'll subtract the mean of 0.05, and we'll divide by the standard deviation of 0.02. And by doing so, we're creating a standard normal random variable, and then we can use the tables the way we always have. All right, now before we do that though, I want to show you why this is working. You've got you've got the normal distribution for the stock, and the mean is 0.05. And the standard deviation is 2, so 0.07 would mean 1 standard deviation above the mean. 0.09 is 2 standard deviations above the mean. For down here, we have 0.03, oops, 0.03. One standard deviation below the mean. And then finally, right about here, we have for 0.01, 2 standard deviations below the mean. Now, this is the distribution for X. Now, for the corresponding standard normal distribution, Z, let me try that again. The mean is 0. This term represents 1 standard deviation above the mean. And this is 2. This is -1. And this is -2. So basically, like if you pick any one of these at random, suppose I wanted to know the probability that the return of the stock is less than, let me put this over here somewhere. 7%, it would be equivalent to saying, what is the probability that Z is less than or equal to 1? Because you can see they both represent being 1 standard deviation above the mean. And so you could say the same thing about 0.09. The probability that X is less than or equal to 0.09 is the same thing as the probability that Z is less than or equal to 2. And so all of the values above correspond to the ones below. And again, like to me, the best analogy for this is converting from Fahrenheit into Celsius. It's the same information with different units. But the table is based on the standard normal. So this is why this is necessary, because otherwise you will not be able to use your tables. So you can go to the table and look for 0.07, but it won't be there. But 1.0 will be there. Okay, so that's why we need to do this. So once that's done, the rest is very simple. So for example, in part A, the probability that X is less than or equal to 4%. So if you notice, remember the formula is Z equals X minus mu over sigma. So this 0.04 is what you were given. This is the mean, and that's the standard deviation. Remember, X has a mean of 0.05 and a standard deviation of 0.02. So you're taking the number that you're actually looking for, which is 4%, you subtract the mean of 0.05, and you divide by the standard deviation. And so it turns out that X being less than or equal to 0.04 is equivalent to Z being less than or equal to -0.5. In other words, in both cases, 0.04 for X and -0.5 for Z are 1/2 standard deviation below the mean. Okay, so well, I don't think I have enough room here, but I'll give it a shot. All right, they're not perfect, but you can see that the 0.04 on the X distribution is the same as -0.5 for Z. And that we can look up in the table. So now clearly this one is right on the table, so we can go look it up ourselves and confirm that on the negative table, -0.5 this can be rewritten as -0.5 plus 0.00. Okay. In fact, we really should write this like this, but it's the same thing. And so the -0.5 is way down here. And the 0.00 column is this first column. So we end up with an intersection of 0.3085. And that is in fact our final answer. We're done. Both of these probabilities are 0.3085. And we're done. So the key to the whole thing was this. This was the extra step that we haven't needed before. Once that's accomplished, the rest is exactly what we've been doing. So I still keep coming back. Again, it's like saying, what's the probability that the temperature tomorrow will be less than 32 degrees Fahrenheit is equivalent to saying, what's the probability that it'll be less than 0 degrees Celsius? So if you had a chart of Celsius values, you would convert the Fahrenheit to Celsius and you'd be all set. All right, now how about greater than or equal to 0.08? Now this one's a little trickier because it's a greater than or equal to problem, but no, it is not difficult at all because remember, we're just applying this formula. And because X has a mean of 0.05 and standard deviation of 0.02, this Z formula will actually become X minus 0.05 over 0.02, which you can see right here. Since this time the value of X is 0.08, this is equivalent to saying what's the probability that Z is greater than or equal to 1.5. All right, so let's see if I can sneak it in here. Everything above 0.08 and the X distribution is equivalent to everything above 1.5 in the standard normal distribution. Now, because it's a greater than or equal to probability, we have to use this approach. 1 minus Z1 less than 1.5, and then this number comes from the table. In fact, let's go look it up and confirm that. 0.9332. All right, here we go. We need the positive table this time. We're looking for 1.5. So 1.5 is right about here. And 0.0 is here. There we go, 0.9332. But of course, that's not what we really want. We have to subtract 1 from that. In other words, the unshaded region here is 0.9332. So the shaded region, which is what we really need, is 0.0668. And that means that's true of the X distribution as well. So it's a very small probability. In other words, the return of the stock is not likely to go up that high, given that the mean is 5% and the standard deviation is 2%, but it's still possible. All right, now the last one will involve in between 4 and 7. So we apply the same formula, subtract these values and divide from these two. And that means that this setup for X is equivalent to being between -0.5 and +1 with the standard normal distribution. Okay, so this is what we're going to work with. And of course, that means we're going to take the difference between these two each of which we can look up directly in the tables. Okay. All right, so I guess we can do that to get a little practice. 1.0 is this one. The intersection of 1.0 and 0.00 is 0.8413. The -1/2 comes from the negative table, of course. -0.5 is the same. Oh, it was already right there. We used that before. How do you like that? 0.3085. So whatever that difference is the probability that we need. 0.5328. Okay. So those are the three cases. And so now we're going to introduce a very interesting application of the normal distribution here. Now, it turns out, I just want to, before we even do this, I just want to mention here that if you are looking at the binomial distribution very carefully, with a histogram, you'll notice something interesting about it. Now, we've already seen histograms for the binomial distribution, but what I'd like to point out is this. If you have enough trials, the histogram starts to look something like this, and you notice that starts to resemble very closely something we've already seen. Oh, look at that. The binomial distribution, as we keep increasing the number of trials, starts to very closely resemble the normal distribution. Okay, so as the number of trials increases, the binomial distribution more closely resembles the normal distribution. Now, why does that matter? Well, here's why. That being the case, for situations with a large number of trials, the normal distribution can be used as an approximation to the binomial distribution. And that's what we're about to do right now. Okay, we're going to see how this can be done. Now, I just want to mention here, here's an example of when this might come in handy. Suppose that a coin is flipped 1,000 times. The coin flipping experiment is a binomial experiment, so that x equals the number of heads is a binomial random variable. Suppose we want to know the probability of getting between 400 and 600 heads. Well, there's nothing to stop us from doing that. We can certainly do that, but this would require us to calculate the probability that x equals 400 plus 401 plus 402 plus wow, that's a lot of calculations. So you can see that this could take a long time. Now, at this point in time, you know, if you're using computers or Excel or whatever, that wouldn't be such a big deal. But at a point in time when there were no computers, this would have been a major headache. So in a case like this, if we only need an approximate result, it would be much quicker to use the normal distribution to solve for this probability. Now you're probably saying, well, how can we do that? How can we apply the normal distribution to this result? Well, the answer is we can. There's a way we can do this with the understanding that it's only an approximation, but it can be done. And by the way, this could also be done for the Poisson distribution, but we're only going to use the binomial. So how would this work? Well, first of all, let me catch up here. First of all, we're only going to use it for cases when we have a large number of trials, and the probability of success should ideally be relatively low. If not, the approximation will not be quite as close, although we can still certainly do so. And so we'll assume that when we use this approach, we've got a large number of trials and the probability of success is relatively low. So let me show you a quick example of this. So here's a good one. Suppose we have a situation where it turns out that 8% of all people have type AB positive blood. Now, we have a class of 60 students. We want to know the likelihood or probability that somewhere between 3 and 7 of them have type AB positive blood. Now, by the way, just as a side note, the reason why we can use the binomial distribution here, we know that there are many different blood types, more than 2. The standard blood types, well, you probably know this from high school biology, are A minus. Wait a minute. No, I think it's if you're A, it's either A minus or A plus. There's no plain A. B minus, B plus, O minus, or O negative, I guess we should say. AB negative, AB positive. Okay. Does that look right? Yes. So here's what we're going to do. By treating everyone as having AB positive, or I guess we could think of it as one of the other blood types. In other words, everything else. This can be treated as a binomial experiment. So in other words, in spite of the fact that there's more than 2 blood types, by thinking only in terms of either you have AB positive or you don't, we can still use the binomial distribution for this particular problem. So if you're wondering about that, this is how we can get around that problem of only 2 outcomes, by thinking in terms of either AB positive or not AB positive. And also, you can tell that the blood types of the people in the class are clearly independent of each other. I mean, unless you have identical twins in the room or something like that, but basically they're all independent of each other. And in addition, the probability of having this blood type is the same for everyone. So this can be thought of as a binomial experiment that we're conducting. And each individual in the class is a trial where you either have it or you don't. And if we think of AB positive as a success, then the likelihood or the probability is 0.08. Remember, probability of success, we are using the letter pi to represent that. So imagine, like, if for some reason the local blood bank desperately needs donations from people who are AB positive. That's why this might matter, because they only need AB positive. So they're going to try to find out who's available to potentially give blood. And so we want to know what's the probability that somewhere between 3 and 7 have AB positive. And the trials, by the way, remember, we're designated with the letter N. Okay, so N is 60 and pi is 0.08 because there's 60 students, and pi, the probability of having the AB positive, is 0.08. Now, calculating this probability would mean calculating all of these individual binomial probabilities and adding them up. That's not that many, but it's still a lot of work. So we want to try a quicker approach that will give us an approximate answer that's pretty close. Because if you notice, we do have a fairly large number of trials and the probability of success is fairly small. So now here's what we have to do though. Because we're using a continuous distribution to approximate a discrete distribution, there's one step that we have to do first. And what we're essentially doing is adjusting the probability that we are calculating. So what exactly does that mean? Well, in this case, we're looking for the probability that the number of students with the type AB positive blood is between 3 and 7. So in order to improve the approximation, we're going to make two small changes. We're going to change the lower limit by subtracting a half from it. And we're going to change the upper limit by adding a half to it. So in this case, the probability that X is between 3 and 7 will be rewritten as the probability that X is between 2.5 and 7.5. Okay. Only because it seems to make this process work better. All right. Now for single values, see, now this is one of the awkward pieces, awkward ways or things about this approach. With a discrete distribution like binomial, we can calculate the probability that X equals 3. But we can't do that with a continuous distribution. So the way we work around that is to turn the single probability into an interval. That's one of the awkward features of this. So if you were asked, let's say the probability that there's 3 students with type AB positive blood, you could rewrite it like this. Although in a case like that, if you only need one probability, you probably would just use the binomial distribution anyway. There'd be no real need for this approximation. But if you did, this is how it would work. Okay, let's see. All right, let's work through this example. And let's see. So the 3 to 7 is converted into 2.5 up to 7.5. Now, you'll recall, of course, that when we used non-standard normal random variables, we converted with this formula. We're going to do something similar here, but there's an important difference now. What is that difference? Okay, here we go. Just a quick reminder. You might remember that for the binomial distribution, now the expected value is the same thing as the mean. And we remember there's a special formula for that, which was n times pi. The standard deviation is n pi 1 minus pi. Okay, that's just a quick reminder from chapter 6. Why does that matter? Because we're going to need to convert our binomial random variable into a standard normal random variable, and we'll be using these values to do so. In other words, this formula that we were using earlier is going to be replaced with this one. So you notice how the mu becomes n pi, and the sigma becomes n pi 1 minus pi. Well, for our specific example, what that means then is that if you recall, we had n or 60 students, or n equals 60, and the probability of having that blood type was 0.08. So now these values, n times pi, or the mean, is 60 times 0.08 or 4.8. The standard deviation is 60 times 0.08 times 0.92, which is 2.101. So for each of the probabilities that we'll be calculating, we'll be subtracting 4.8 from x and then dividing by 2.101. Okay, so the only thing that's really different is that the mean and standard deviation are coming from the binomial distribution rather than the normal. All right, so let's take a look and see how that works. So with this interval, what I'm going to do is subtract, as we said, 4.8 and divide by 2.101. And when we do that, whoops, it turns out this is equal to approximately negative 1.09 up to 1.29. So in other words, the probability of getting that many students with the type AB positive blood is approximately equal to the probability of Z falling between negative 1.09 and positive 1.29. So this is what we're looking for. And of course, that means we're going to do a subtraction after looking up these values in the tables. Okay. Now it's just a question of looking them up in the table. So I've already done that in the next slide, but we'll go back and double check it for practice. Okay. Now this part we're very good at. We're already experts in looking things up in this table and coming up with probabilities. So let's do that right now. We'll make room for it up here. All right, so for 1.29, we'll go to the positive table. And we will find ourselves the intersection of 1.2 and 0.09. And where do they intersect? 0.9015. How about the negative 1.09? All right, let's find out. Let's get rid of these. Okay, oh, and these two. So we need negative 1.09. And so let's see if we can find that here. Yeah, here we go. Negative 1.0 is here, 0.09 is here, and they intersect at 0.1379. Okay. So the difference between the two is 0.7636. So that's our approximate probability that somewhere between 3 and 7 of the students in the class have AB positive blood. All right, now I also went ahead and calculated the actual probability. So remember, we got the approximate probability is 0.7636. The actual binomial probability is actually 7639. So you can see in this case, it did an excellent job. So just in general, if the expected value, now remember, we got an expected value of 60 times 0.08. It was 4.8. It's not quite 5. It was very close though. But here, ooh, boy, that's a big number. 60 times 0.92 is 55.2. So when both of these are greater than 5, just as a rough rule of thumb, we should expect to get very good results. If not, the results will be less impressive. They'll be not quite as close, but we can still use this. So for some applications, this could be a very helpful first approximation to the actual value. Okay. Now, what about a case like this? The probability, the number of students with AB positive is no more than 6 or less. Okay. Instead of an in-between probability, we're looking at less than or equal to. So the only thing that's different is that we only have to use one adjustment. In other words, the continuity correction only applies to the upper limit in this case. We only have to make one adjustment. So that less than or equal to 6 becomes less than or equal to 6.5. And we don't have to worry about the lower limit. And so the rest of the steps are exactly the same. So we're looking for the probability that X is less than or equal to 6.5. Now, the rest of this is the same. Z is going to be equal to X minus 4.8 over 2.101. And when I apply that here, you can see I've got the probability that Z is less than or equal to 0.81. Well, that's easy because it's a cumulative probability. I can just go right to my table. And when I do, let's go find it. I'm looking for 0.81. So 0.08 is here, 0.01 is here. 0.7910 is our final result. Okay. And that's it, you're done. Now, by the way, don't forget, if you've done this with the binomial distribution, you would have left it at 6, but that would have meant calculating all of these probabilities. And if you did that, I think I have the actual answer here. Yeah, 0.7980. So, it's off a little bit, but it's really not that much. And again, it might be a nice time saver. Okay. Now, how about this last one? At least 4 have type AB positive blood. Now, this is the lower limit. By the way, this can be written as this. So now 4 is the lower limit. We're not going to use an upper limit. We're just going to think of this as the continuity correction will drop the lower limit by 1/2, and then we'll leave the rest the same. Then we'll apply the same conversion formula. Z is x minus 4.8 over 2.101, and then we'll take it from there. All right, so let's do it. So you can see the 3.5, we start with this, and we convert. And now we have Z is greater than or equal to negative 0.62, which of course is the same thing as 1 minus Z less than negative 0.62. And we can go back to our negative table and find that one. So negative 0.62, of course, can be decomposed into negative 0.6 plus 0.02. And we'll end up with right about here, just barely fits. Negative 0.06, 0.02, 0.2676. So 1 minus that, of course, would therefore be 73.24. So this time, the approximation is a little bit worse. The exact probability is 0.7171, but still it's not that far off. You know, a lot of this depends on how much accuracy we really need compared to how much time we're willing to spend on this. So, you know, this is one of those situations where using this approximation is always optional, but sometimes it can really save a lot of time and still give us a very good answer to our question. But again, I mean, when we didn't have access to things like Excel or calculators or computers, this would have been a much more helpful time-saving device. All right, now, believe it or not, we're completely done with 7. And by the way, I forgot to save this. Hold on. So, you know what, we're really zooming it. I'll tell you what we have to start thinking about, and I guess sometime next week, we really have to start thinking about the first midterm. Now, the midterm, of course, will be done at home, just like your assignments. But, you know, before we actually have it, we want to go over and do together in class what I call my sample midterm. And it is a set of questions that's exactly like what we've been doing. And it'll be very similar to the actual midterm. And since we only have like 2 weeks down and 2 to go, basically, I think it's getting time that we have to start thinking that possibly as soon as next Tuesday, we should at least consider going over the sample midterm, Tuesday or Wednesday, so that you can have a lot of time to actually work on the midterm. So we'll figure that out. But I think sometime early next week, I will post the sample midterm. In fact, I guess it's already right here. Let me just see if it's all right. So what I'm seeing here is that, oh, I see why we waited so long. Okay. Yes, this required us to be completely done with chapter 7, which we are right now, by the way. So sometime next week, we can go over this, and you can see it's fairly long. But that's because we're trying to cover all the good stuff that, ooh, look at all this good stuff. What this one would not be meant to be collected. This is something you should work on at home, and then we will go over it together in the class. Because otherwise, you know, we really do need to make sure that everybody's on the same page, that everyone understands what we've been doing. And we've only so far had the one assignment. So we'll do this maybe next Tuesday or possibly Wednesday. So first things first, let me post it before I completely forget. That could happen. So you have a chance to look at it, you know, sooner rather than later. First, let me go find Moodle. There we go. Now, everything else you need. Oh, you know what else? I haven't posted 8 yet. I wanted to make one small change to it before I post it. That's why it's missing. And then today we did the rest of 7. So let me post today's version so that we'll have a complete set. Now, you know what we're probably going to have to do is, so far we've only had the one assignment. Now, I've already announced that chapter 5 problem set is due on Tuesday. You know, this might seem like a bit of a rush, but why don't we do this? Because the problem sets are really not that time consuming. Just because we don't want to run out of time. Wow. I'd really like to go over the sample midterm next week. So let's do this. So the sample midterm will be based on chapters 3, 5, 7, 6, and 7. We will go over it in class next week. You do not need to hand it in. All right, I want to make that crystal clear right now. Once we have finished it, I will post the actual midterm, and you will have at least a week to complete it. Yeah, we'll figure it out, but you'll have plenty of time. Now, in the meantime, though, just to make sure we don't lose any time, the holidays, you know, of course, have been sort of getting in the way, but why don't we do this? Let's have the chapter 6 problem set. To do this to you, but let's have this due next Wednesday, which is, God, I don't know. Let me look at the calendar. Looks like next Wednesday is the 5th. Okay. And then the chapter 7 problem set can be due the following Monday, which is January 10th. So remember, our last day is the 17th. So we shouldn't run out of time. I just want to make sure we squeeze all this good stuff in. Okay. All right. So it's getting a little busy, but you know what, with the holidays being behind us, more or less, that shouldn't be a problem. And so sometime during the week, we'll start diving. Now, this sample midterm is quite long, as you saw. It might take up the entire class. Maybe not, but it'll take up a lot of it. And so now, of course, once I post the midterm, you know, it'll be due roughly a week later, but you'll always have the opportunity to ask questions by email, and you'll always have the opportunity to ask for a Zoom session if you're stuck on anything. But I believe that everything in here is pretty much, oh, you know what? I just thought of something. I hope I didn't include, remember we decided not to do Bayes' theorem? Oh, let me just see if I left that in the sample midterm. Ooh. If it's there, then you don't have to worry about it. Let me just see if it's there. No, no Bayes' theorem questions. All right, that's good. Okay, so I don't have to delete it. It's not there, so we're good. So everything here is just what we covered, and you can see, man, we've done 2 weeks in, and look how much material we've covered. Look at all this stuff. Man, we are really zooming. Wow, that's pretty impressive, I must say. So you've done a great job learning a lot of complicated material, I must say. So you should congratulate yourselves for getting so much work done in such a short time. But anyway, all right. So I think we're all on target here. So we'll have that way the problem sets, we'll be catching up with them. And then, you know, so what we'll probably do is on Monday, we'll start chapter 8. And then maybe Tuesday, we'll start to maybe introduce the sample midterm. Maybe we'll split it up over 2 classes, but we'll definitely get it done next week so that you'll have plenty of time to finish your midterm. And we'll carry on from there. Now, we only have 3 more chapters to go, but they're fairly involved. So it may sound like it's not much, but you know, as you can probably guess, the chapters do get a little messier as we go along. Luckily, though, those last 3 chapters depend very heavily on the normal distribution. So that means you've already got a lot of background material that you need to really understand those next 3 chapters. So that will help a lot. Having already seen the normal distribution will make these last 3 chapters much easier to follow. So, all right, I don't think there's any point in starting something new right now with 7 minutes left. So I think we'll stop it right here. I've made all the announcements. I've posted all the new notes. The only thing that remains is the video. Now the video, sometimes it takes quite a while to process it. I will get it out there as fast as I can, but it can take a while. So other than that, I think we're good for next week. So just for next week, oh, as far as the problem sets go, you can just put all your answers on a piece of paper. You can write it by hand or type it if you are able to do that. And then what you should do is just take a picture of it with your cell phone or use one of those scanning apps that I mentioned at the start of the course, and then just email them directly back to me at my purchase account. Ideally, if you forget and send it to my Gmail account, that's fine. I'll still find it. But just be aware that these files can be very large and they could get trapped in my junk box. So I will go through and make sure that I can find them all. And if I can't, I'll just ask you to resend it. Okay. So yeah, just type out the answers or write them out as if you were in a classroom setting, and then take pictures of them or scan them and send them back to me. Okay. All right. So does anybody have any last minute questions? Well, do you want to do it right now when everyone's done?
That could work.
Okay.
If you're available.
All right. Let me go open it up. In fact, other people might want to stick around for this anyway. Second question of chapter 5. All right, let's get that out. For everyone else, you can just, we're done. We're just going to quickly review the chapter 5 problem set. Oh, this one. Okay, so what would you like to go over?
So the part that I'm confused about is because I was looking over the notes, but what I've noticed is that in here, whenever I look for how to get that, whatever that's called, so what ends up happening is I run into a formula that basically it's easier if I show it to you. I'm just gonna pull it up right now.
Okay, I think you can share your screen if I turn off my screen sharing. So I'm going to do that right now. Okay, I hope that'll let me back in though. All right, I'll tell you what, let me hit the stop share button. I'm pretty sure that will allow you to show me what you're doing. Okay, so now you turn on the screen sharing and I believe it'll show me what you're doing on your screen.
It says disabled.
Oh, I forgot. I have to turn that on. All right, try it now. There we go. All right. So we're looking at.
So I'm trying to.
Oh, yeah.
Yeah, I
So,
wasn't sure which formula to use to begin for the second one.
Okay. All right. Here's what you have to do. S given D. So what you're going to do is it's a ratio. You're
Yes.
going to have S intersect D, which, by the way, you can, with the intersection symbol, you can use the word and instead of it.
Oh, okay.
So you can type S and D.
Or something like that.
Okay. That works too. Divided by the probability of D. Oh, actually, the one on the left, you should keep the bar there. Yeah, put the bar back. No, wait a minute. Oh, wait, I understand now. I'm sorry. I misunderstood. Go back and take away the and. See where it says S given D. Change that to and after all. I was thinking of the wrong problem. So put the ampersand. Now, with a table in front of you, that number is in the table. The intersection between S and D is the probability that you're looking for.
Oh, so I would look for that.
Yes, and you literally just copy that number. It's just 0.12.
Okay, so there wasn't any particular formula that
No, there's no formula because it's already there.
Yeah, I was confused for a moment.
Right.
So
well, now there is a formula, but we don't need it here. Instead, you can just read it right off the table. So the answer is just 0.12 because it's right on the table. Yeah, you don't need the P there. Just put 0.12. I mean, that's literally all you do. Just get rid of everything else and change it to 0.12.
Okay, that's easy.
Yes, you're done. So all the intersections are read straight off the table.
Oh, okay, that makes sense.
Okay. And also the single probabilities, S and F, those are column or row totals.
Okay, so I think I can figure out the rest of it from now on. But that was really
all right. No, I guess that what I see what you mean. It was maybe not as clear as it could have been, but yeah, in this case, because you already have the table, for those at least, you don't have to do a formula. All right. Was that the only question you had?
That should be it for now. Thank you.
Okay, good. If that's all you have trouble with, then you're in good shape. All right. Anybody else? All right. Then I'll see you all next Monday. Okay. Bye, everyone.